Hello, my name is Ikinjano Fuktepe, and I'm a postdoc researcher at University of Missouri, Columbia. And today I will be presenting our presentation and paper named as pyTAG, a Python-based interactive training data generation for visual tracking algorithms. The presentation will start with an introduction and then follow up with a problem definition that has been tackled in our paper. And then we will introduce our tool, which has three modules: the ground truth generation modules, the editing module, and the reviewing module. We will then actually evaluate and compare the other tools with our tool, and then discuss the differences between these tools. And we will finalize the presentation with the conclusion section. So it is well known that machine learning based algorithms in the object tracking method field is getting really popular. And machine learning based object tracking methods in all other terms, they all require a training data, in other words a ground truth data to train these methods. On the other hand, there are competitions for object tracking methods, which can be, for example, they can be given as MOT and VOT, and they evaluate the performances of these object tracking methods by ground truth data and decide on the winners. So these competitions are really valuable for the society because it pushes the researchers really hard, and it is known that the recent object tracking methods, the state of the arts, have actually emerged from these competitions. So that's why they are really valuable to the society. And there's also one other fact that from the recent winners from I think the VOTC challenge were mostly deep learning based trackers. So this is also another sign that machine learning based algorithms in object tracking methods are getting really popular. Also, not only for the challenges, like how they are actually evaluated, it is also important for researchers as well. When a researcher wants to evaluate and compare their object tracking method with other methods to see if they're performing better or worse, they have to require the ground truth data to compare their results. And it is actually an essential process for the researchers. So coming to the problem definition, I want to give a couple of examples from our research lab that we have actually experienced recently. So a couple of months ago, we have received a data set from one of our collaborators where one of the video had like 400 frames, and they wanted to test our one of our object tracking methods and see how it actually performs. So while generating the ground truth data manually, it took approximately 3 to 4 hours, and this actually can vary based on the frame quality, and like if it's blurry or it has a low resolution, it becomes even difficult to distinguish the object and its shadows, and that could even increase the time of generating the ground truths. So on the other hand, there is also one more thing. In the research lab, we have we have actually plenty of graduate students who are performing their research, but in such cases where we actually require ground truths, they need to focus on generating the ground truth, which requires a lot of focus actually, and they have to leave their research, and that's probably one of the things that we don't want actually. We don't want to allocate our resources in our lab for ground truth generation. There is also one more problem that we might encounter is the ground truth generation approach that some of the existing tools use, such as linear interpolation, object tracking, by using object tracking methods, or time-based regression or homography representation. So these also have their own advantages and disadvantages, and some of them may not be appropriate for every scenario that we have. So related to the problem definitions that we have given, we have developed a tool called pyTAG in order to solve these issues that we might encounter. So pyTAG it stands for the Python-based Tracking Assisted Ground Truthing tool. And it has three major models where it has a ground truth generation module, an editing module, and a reviewing module. And the good part is about the pyTAG, it has three modes. And the first mode is using the tool as a fully manual ground truthing tool. And the other one is the second mode is the assisted mode, where it is actually a semi-automatic approach while generating ground truths. And the third mode is the fully automatic approach. And when we talk about the ground truthing generation module, it has a couple of approaches. You can use linear interpolation, which is actually semi-automatic, and you can use an object tracking method, which can be used as a fully automatic or a semi-automatic, or even you can use a reviewing module to actually draw bounding boxes for each frame, which will actually stand for a fully manual approach. So when we get into detail the proposed tool, I want to list the functionalities that we can do with pyTAG. So the ground truth generation module, as we mentioned, has a linear interpolation based generation module, and it can also be generated by using object tracking methods, which includes currently 6 trackers. And the editing module, which only applies for the object tracking methods approach for the ground truth generation model, it requires interaction on the object tracking methods. And these can be listed as frame navigation, which allows us to move back and forth on the frames, and pausing and resuming the video, reinitializing the bounding box, restarting the tracker, and also it allows us to change the object tracking method during generation. And also we have the reviewing module. So when we actually generated the ground truth data or the training data, and if we want to actually make some like minor fixes, we can use the reviewing module as well. So the architecture of the proposed tool, as we mentioned, the blue part that you can see in this presentation stands for the ground truth generation module. And as we mentioned, the orangish and like kind of yellowish part that you see in the architecture is the editing module, which is a part of the tracker-based ground truth generation. And the green part is the reviewing module that has been given here. So all of these modules require the same process where we upload image frames, but there's also an additional process that we need to follow in the reviewing module where we upload the bounding box information. So the output of these two modules, the ground truth generation, the reviewing module, has actually generate a bounding box report. So let's start with the ground truth generation with linear interpolation. So it's actually a straightforward approach, and it's a well-known and used approach in other tools as well. It requires 2 actions from the user. As we mentioned, it's a semi-automatic approach. First, the number of frames that will be skipped should be determined given by the user, and at every skipped frames, the user should draw the bounding box, and then the tool will actually generate the bounding box in between those frames that has been skipped. So we have a diagram that shows how the linear interpolation works. So we actually use the 2 corners of a bounding box, which is the left top corner point and the bottom right corner. And we calculate the distances between the 2 bounding boxes for the corresponding points. And then we divide them by the number of frames that has been skipped, which will actually and when they're actually divided, we will calculate the points for every frame that's going to be drawn by the linear interpolation. In this slide, you will see a demonstration of the linear interpolation based ground truth generation where the frame skip size is set to 30 frames. So approximately it should take 12 actions of drawing bounding boxes for this given 300 frames. And in the next slide, you'll actually see the demonstration of this ground truth generation process. So in this slide, we are actually seeing the linear interpolation based ground truth generation where the frame skip size were actually set to 30 frames. So as you can see, the linear interpolation is not that bad, but except for the occluded part that we've seen in the video. So the other part of the ground truth generation by using the object tracking method. So we have actually used six object tracking methods that were provided by OpenCV. So those are boosting, CSRT, KCF, median flow, MIL, and TLD. So since that we've used OpenCV's object tracking methods, the design of the OpenCV uses actually a strategy pattern where there is a superclass called as tracker, and the functions inside the tracker are actually inherited by the subclasses. So this actually provides us the strategy design introduced by the OpenCV gives us this opportunity to introduce another object tracking method. So we actually have two ways to extend the trackers here. Since that pyTAG is developed in Python, we can also introduce a Python written object tracking method such as SciMDW, which is also the current state of the art object tracking method. And also, since that we're using OpenCV Python, so this means we are actually using the C++ version of OpenCV, and this means that we can also introduce a C++ written object tracking method into OpenCV and then recompile it and do the necessary binding between the Python and the C++ code, so we will be able to use that object tracking method as well. So in this demo, we will actually show you how the object tracking method can actually be changed during a ground truth generation with object tracking methods. So as we mentioned, we have 6 object tracking methods here, and we're actually switching to all of them in this video example that you can see. So in such cases, we can actually change the object tracking method that is more beneficial for us, and that we can actually use it for our advantage. And you can see that we can actually perform this object tracking method change during the ground truth generation. So there is also this interactions that we can also make during ground truth generation. It's not limited to switching the object tracking method, but in some cases the object that we're tracking can be lost and can be occluded, and these can actually cause the object tracking methods to fail. And these fails will end up generating faulty ground truths and training data for us, and we want to actually be able to fix those bounding boxes during generation. So we have a couple of interactions that we can make. As we mentioned before, you can actually go back and forth on the images, and we can actually pause the video, and then we can actually reinitialize the bounding box, change the object tracking method as well, until we have set it to a point that we want it based on our interest. So this is actually the state machine diagram that is given for the interaction that could be made while generating ground truth with object tracking methods. So in this example, we wanted to show you the other editing features that can be done with the ground truth generation with object tracking methods, where we can actually navigate the frames. So for example, we are currently moving a couple of frames back, where the object is actually occluded, and now we will actually move a couple of frames ahead. So we're moving the frames ahead until the object is clear and reinitialize the bounding box for the object tracking method that we want to use. And we can actually sometimes we can actually generate faulty some bounding boxes, and we can actually fix those by pausing it and resuming with the new bounding box that we've actually set. So in the next slide, we will actually see the demo of the ground truth that has been generated from this process now. So as we mentioned, in this demo, you're seeing the previous ground truth generation that we have done. So this is the output of after the ground truth generation. So you can see that there is some gap where there is no bounding box. So that is the part that actually corresponds to the part that we actually skipped a couple of frames ahead. And therefore, when we actually skip a couple of frames, it is replaced with zeros, which means that there is no bounding box for the current frames that has been given. In the reviewing module, as we mentioned again, we want to actually fix the faulty bounding boxes that has been generated by the object tracking methods, or it could be generated by the linear interpolation. So we will see how we can actually fix these bounding boxes. So in this slide, now we'll actually see the reviewing process that can be done on the existing ground truth data that has been generated by the object tracking methods or the linear interpolated ground truth data. And so remember that in this actually video, there are some parts that there were missing bounding boxes. There were faulty bounding boxes like we're currently trying to fix now. And there's going to be occluded parts of frames where there wasn't supposed to be any bounding box at all. And there's also another place where the object tracking method is actually tracking another object. So we're going to also fix those as we can cache them. And now currently we are adding the new bounding boxes that was supposed to be in the video. And at the end of this reviewing process, we will be able to generate a new bounding box data, and in the next slide we will actually see the output of it. Here we can actually see the output of after the reviewing process. So the red bounding boxes correspond to the original version that has been generated by the tracking methods, which can also be linear interpolated version of the bounding boxes. And the green bounding box that we are seeing right now is after the reviewing part that we have actually fixed, where we actually added or edited the existing bounding boxes. So in this section, in the evaluation and comparison, we have performed our evaluation comparison under 5 criteria. So these 5 criteria are the platforms, if it's a web-based or a desktop. We compare the programming languages that they've been developed with, and we looked into if they have actually supporting frame navigation in the video. And we also looked in the type of annotation propagation that they have used, and we also looked into if they have actually have a reviewing module that they're supporting for the users. So we have compared and evaluated 11 additional ground truth generation tools. So these are FlowBoost, GTTool, GT2W, GTVT, InterOD, IVAT, Column, LabelMeV, Vatage, Viper GT, and Firefly. So here's a table where we are showing the comparison and the criteria that we've actually evaluated. So starting with the platform, we can see that there's only 4 tools that are working under a web-based platform, while all of the others are desktop-based platforms. And when we look into the programming language, we can see that C, C++, and using Qt are actually quite popular, and also Visual Studio.NET, C# as well. But of course, the web-based applications, the tools, are developed in a more like script languages and like server-side code or client-side code, which can be JavaScript, Python, or Adobe Flex and PHP. The only different tool, the programming language that you see is ViperGT and pyTAG, which ViperGT is written with Java and pyTAG is written with Python. So when we look into the frame navigation, we can see that almost every of these tools are actually supporting frame navigation except for GTVT, but FlowBoost we didn't have enough information to include it in our table. When we look into the annotation propagation, at first sight we can see that using object tracking methods and linear interpolation has been quite used a lot. So we can see that linear interpolation, except for we're not going to include pyTAG. So there are, I think, 3 tools that uses linear interpolation, and also 3 other tools that uses object tracking. And when we look into pyTAG, our proposed tool, it actually supports both of these annotation propagation options. And when we look into the reviewing feature, it is quite interesting that there are tools that they do not support a reviewing module. And those are like Vatich, Label Me Video, GTTool, and FlowBoost, while the other all tools actually support a reviewing feature. So when we get into discussion, so when we evaluate this, so we have only seen that only 3 of the tools were developed in web-based platforms. So this might be a good focus for other researchers to develop these tools for web-based platforms, because normally developing these tools under a web platform might have limitations, like related to performance issues that we might encounter and the number of users that might use at the same time. So in those cases, now we actually have a lot of web services and cloud solutions to actually handle these types of problems. So that will probably solve the issues for the web-based platforms for these types of tools. And when we looked into the object tracking based methods, that they're using object tracking methods for ground truth generation, and only 3 of these by discarding us. So if we include all, so there will be 4 tools that actually support object tracking methods. And it's quite interesting that the web-based developed tools doesn't use linear interpolation or object tracking methods for ground truth generation or training data generation. And they've mostly focused and used different approaches. Some of them are just manual, and some of them are using homography presentations. But another thing, when we look into the other criteria, so when we look into frame navigation, almost every tool supports frame navigation. So it looks like the frame navigation is actually an essential part for these tools and for the usability of the tools for generating ground truth. And similarly as well, except for the 4 tools, the remaining other tool, the 8 tools that we've seen, have a reviewing feature. So we also think that the reviewing feature is actually quite important, because most of the automatic ground truth generation tools do not perform very well, so it might require a little editing and reviewing of these ground truths. And when we actually looked into details of how these tools are actually developed, they've used incumbent in object-oriented language like C++ and C# Java. This is probably by utilizing some of the power of object-oriented paradigm. So by this, they can actually use some of the design patterns, such as like MVC and observer patterns, which are meant to solve user interaction issues that might occur. So in conclusion, best to our knowledge, pyTAG is the first Python-based desktop tool for ground truthing and generating training data. So the important part for pyTAG is it has been developed and designed in a manner that can be extended with multiple object tracking methods. So you can actually introduce more object tracking methods in order to generate ground truths in an assisted mode, in a fully automatic mode. And probably this is the most important part about pyTAG, that it supports 3 modes. So you can go fully manual, or you can generate your ground truths in assisted or a fully automatic mode. So this gives in multiple options for the users, because not every fully automatic approach for ground truthing is the best. In some cases, you require you need to introduce. You need to actually intervene and handle some cases, and in some approaches, going manually might even be better compared to other fully automatic approaches. So we are trying to give as much as possible ways to generate ground truths for the users. Another important thing about pyTAG is it's a small, lightweight tool. It only has one dependency, which is OpenCV, and it's approximately 500 lines of code. And the last thing about pyTAG is it also includes the Python users to easily use and modify the tool for their advantage. Thank you for listening to our presentation. I'll be really happy to answer your questions through the forum. And also, I would love to read if you have any suggestions that could actually improve our tool pyTAG. And we will love to hear any of your recommendations. Thank you again for listening.